Now we have some remark. Suppose P is a partition of the rectangle I. So we always have this inequality, okay? Because the lower integral is the supplement of all lower sum. So this is true. And as we mentioned and proved, lower integral will never greater than upper integral. And upper integral as the infiniment of upper sum, so it will not greater than any given upper sum. So we have this inequality. This means the lower integral and the upper integral always lies between the lower sum and the upper sum for any given partition P. And in particular, if f is integrable, then the lower integral and the upper integral coincide. So the inequality becomes this. Okay, so this is the first remark. The second remark is that we can find a sequence of partition. Because the lower integral is the supplement of lower sum. Upper integral is the infiniment of upper sum. So by the property of infiniment and supplement, they can be approximated using a sequence. The lower integral can be approximated using a sequence of lower sum. That is for some sequence of partition, the corresponding lower sum will approach the lower integral. Similarly, for upper integral, here I have some explained. Here should be pk plus because this might be another sequence. To approximate the lower integral and the upper integral, you need to use different sequence of partition. Okay. Now we have a look at some example. Suppose f is a constant function. What happened? F is a constant function, then we said that f is integrable. And the integral of f over the rectangle is the value, say, the constant function value, say, multiplied the volume of the rectangle I. Okay. The proof is quite easy. Because f is a constant function, for any partition, take any partition, and for every subrectangle belonging to the partition, since f is constant, the infiniment and the supplement are all same. Therefore, you will see that the lower sum and the upper sum are all equal to, say, multiplying the volume of I. Okay, that is the lower integral is the supplement of lower sum, but the lower sum we only have one lower sum. The set consisting of lower sum is actually a singleton set. It contains only one number. So the infiniment is the number itself. So the lower integral is this number. Similarly, the upper integral is also this number. Therefore, they coincide, and the function is integrable. And the integral of the function is precisely this number. Okay. This is the most trivial example. Now we consider this example. Suppose f is defined on a rectangle I, and the definition of f is given here. If x for a point x in I, if all the coordinates of x are rational number, so Qn means that the points in Rn whose all the coordinates of that point are all rational numbers. So if x belongs to the intersection of I and Qn means that x is a point in I whose coordinates x has n coordinates, okay, whose coordinates are all rational. So for such point, we define fx to be 0, and for the other points, we define the value of x to be of fx to be 1. Okay, so this defined a function over the rectangle I. So for this function, for every partition pi and for every partition p and every subrectangle in the partition p, we have the infiniment of f over J is 0. Why this is 0? Because for every such sub-rectangle J, if you contain the points which are rational coefficients, for the points the value of f are 0. So the infiniment is 0. That is, small mgf is 0. Similarly, capital mgf is 1. Why this is 1? Because for every sub-rectangle J, it must contain points whose coordinates are all irrational, whose coordinates are not rational numbers. So for those points, the value of f is 1. Therefore, the supplement is also 1. Okay. So the lower integral of f is 0 because mgf is 0 means that the lower sum of f with respect to any partition is 0. Okay. Therefore, the lower integral is the supplement of lower sum. Therefore, it is also 0 because every lower sum is 0. Okay. Similarly, the upper integral is the volume of I. Why this is the volume of I? Because mgf, capital mgf is 1. So for every partition P, the upper sum of f with respect to the partition P is equal to the sum of capital mgf multiplying the volume of J and sum up. But capital mg is 1. So the upper sum equals the sum of the volume of J, which is the volume of I. Okay, so the upper sum for our function f, the upper sum with respect to any partition P is the volume of I. So the infiniment of the upper sum, that is our upper integral, is also the volume of I. Okay. So because the lower integral and the upper integral are not equal, therefore the function is not integrable. Okay. And now we want to find the if and only if condition for a function to be integrable. Okay. So this is the following very important theorem. Suppose f is a bounded function over the rectangle I. Then f is integrable over the rectangle I if and only if for any given epsilon positive there is a partition P such that with respect to this partition, the lower sum, the difference from the upper sum and the lower sum is less than epsilon. Okay, so this is very fundamental because this describes the integrability completely. Okay, and it is also the starting point to study the integrability of all kinds of functions we will encounter in the future. Okay, so let's have a look on the proof of this theorem. Before proving this theorem, we will give some explanation of the difference of the upper sum and the lower sum. Okay, so for a partition P, given a partition P, suppose J is a sub-rectangle for the partition P, then we denote by omega GF to be the capital MJ minus small mj. That is the supplement of f over J subtracted by the infiniment of f over the J. That is the oscillation of f over the rectangle J. So this small omega GF is the oscillation of f over the rectangle. This is quite natural, a definition. Okay. Then we multiplying the oscillation by the volume of J and sum up, we obtain the capital omega Fp. Okay. Obviously, this capital F omega P is the difference of the upper sum and the lower sum. Okay. So this is called the oscillation volume of F with respect to the partition P. So using the notion of oscillation volume, and our theorem just to show you can be stated in this way. A function is integrable over the rectangle I if and only if for any epsilon positive there is a partition so that with respect to this partition the oscillation volume is smaller than the given epsilon. Okay, now we prove the theorem. The theorem is if and only if, so we prove the only if part first. So we assume that f is integrable. We will prove that for any epsilon we can find a partition so that the oscillation volume is less than epsilon. Okay, so f is integrable means that the lower integral and the upper integral are coincide. Okay, so the integral of f, that is the lower integral of f, is the supplement of the lower sum. Okay, and it is also equal to the upper integral, which is the infiniment of the upper sum. So for our epsilon, using the fact that the integral is the supplement of lower sum, we can obtain a partition such that the integral minus the lower sum with respect to the partition denoted by p minus is less than half of epsilon. Okay, intuitively the integral is the supplement of lower sum, so you can take a corresponding lower sum. You can take a suitable lower sum which is as very close to the integral. Lower sum is less than, is not greater than the integral, but it can very close to the integral for a suitable partition. This is partition denoted by p minus. Okay. Similarly, using the fact that the integral is the infiniment of upper sum, you can take another partition denoted by p plus, such that the upper sum is very close to the integral. So this difference is also less than half of epsilon. Okay. Now, having obtained two partitions p plus and p minus, we take their common refinement. Then this is a new partition of the integral of the rectangle I, and we have, because p is a refinement of p plus, therefore the upper sum of f with respect to p will not greater than the upper sum of f with respect to p plus, because as we said before, defining partition will decrease the upper sum. Okay. And defining the partition will increase the lower sum. So for the partition p, the lower sum will not less than the previous partition p minus. Okay. So using these two inequality, we see that the upper sum and the difference of the upper sum and the lower sum with respect to the partition p will not greater than the difference of the upper sum with respect to p plus minus the lower sum with respect to p minus. Then we use the previous inequality. From this inequality, we see that the upper sum with respect to p plus will not greater than we can write this in this way. We minus this integral, and then subtract this integral, and then add it back to make this an equality. Okay. Then we group the first two terms together, and then the last two terms also group together, and then these two groups are all less than half of epsilon. Therefore, this result will not greater than is less than epsilon. So in this way, from the integrability of f, we construct the partition p, which is the common refinement of the previous partition p plus and p minus, such that the oscillation volume of this partition p is less than epsilon. This proves the only if part of our theorem. Okay, our theorem says that The function is integrable if and only if for any epsilon there is a partition such that the oscillation volume is less than epsilon. Okay, so we have proved the result. So this completed the only if part of the proof. Now we prove the if part.